Hey, AP Chem, welcome to chapter 17. We're going to continue on with this idea of thermochemistry, but here in this chapter is where enthalpy meets the other thermodynamic variables or components. So we're going to introduce a couple more ideas like enthalpy in this chapter, and then we'll see how they influence each other in a chemical reaction. Okay, so what this chapter gets into is an explanation for why some reactions are spontaneous, or why some processes are spontaneous and why some processes are not spontaneous. So that's really the whole purpose that we are going to explore in this chapter. So let's begin by defining what a spontaneous process is. So a spontaneous process is one that can occur when all by itself. If you just leave the components together, if you just leave the process all together, it's going to move forward and change all on its own. Nobody has to come by and introduce heat. Nobody has to come by and shake it up. Okay, no outside action is necessary in order for this process to go forward. It's going to go forward all by itself. That's what a spontaneous process is. Now, this doesn't say anything about how fast a reaction occurs. Okay, a system might move forward on its own in a second, or the system might move forward on its own in 4 billion years. But as long as it moves forward on its own, it's considered a spontaneous process. So this is cautionary tale number 1 in thermodynamics is thermodynamics and kinetics are completely different. The thermodynamic criteria of a process, which we're going to see is going to include enthalpy, and then 2 more things one called entropy and one called free energy. So enthalpy, entropy, and free energy are called thermodynamic criteria. And those 3 together are going to be able to tell you if a reaction occurs, but they do not tell you anything about the speed. The speed of a reaction, how fast a reaction occurs, is going to be considered in our chapter on kinetics. And they are very separate chapters. So you have to divide in your mind this idea between spontaneity and speed. Okay, they don't overlap. They don't influence each other. Okay, they're completely separate. So what we're dealing with in this chapter is spontaneity. We are not dealing with speed at all in this chapter. Okay, another thing I want to talk about before we kind of move on is examples. What are some examples of spontaneous processes? So the easiest, most visualizable process would be a ball on a hill. If there's a ball and it's on the side of a hill, okay, it's going to roll down the hill all by itself. No one has to kick it. No one has to push it. It's just going to roll all by itself. Examples in chemistry would be something like rusting. If you leave iron outside, iron in contact with the atmosphere and the water that the atmosphere contains, the iron is going to rust. There's going to be an electrochemical process where that iron gives up electrons to the water that comes in contact with it. And that iron is going to change into iron oxide. That's a spontaneous process. You can think of marshmallows. If you've ever left a marshmallow bag open, the marshmallow bag is going to absorb water. The marshmallows are going to get stiff and sticky. That is a spontaneous process. It's going to happen left to its own devices. Nobody has to heat up the marshmallows. Nobody has to chew the marshmallows. It just has to be left all by itself, and it's going to happen. So that would be an example of a spontaneous process. Okay, other examples. A ball is going to roll down a hill, but it's never going to spontaneously roll back up the hill. If exposed to air and moisture, steel rusts spontaneously. However, the reverse is never going to happen. Iron oxide is never going to spontaneously change back into iron metal separate from oxygen gas. That will never happen. A gas fills its container uniformly. It's never going to spontaneously compress or collect on one end of the container. Heat flow always occurs from a hot object to a cooler one. The reverse process will never happen spontaneously. Wood burns spontaneously in an exothermic reaction, and it forms carbon dioxide and water. But wood is never going to be spontaneously formed in order for carbon dioxide and water when they're heated together. So here are a couple examples and a couple lessons come out of this. First of all, the forward reaction is going to happen spontaneously. If you look at the reverse reactions of all of these things, they require an input of some sort. Okay, you have to input energy to move a ball back up a hill. You have to input energy in order to change rust and chemically separate it back out into its two components. You have to input energy in order to collect all the gas and compress it on one end of the container. You have to input energy and some magical process called photosynthesis in order for carbon dioxide and water to be combined in the right way, in the right order, in the right sequence, with the right amount of energy input and output in order to form organic compounds like wood. So there has to be some input of energy or supported system, or maybe usually both, in order for the reverse of all of these reactions to occur. So some of these reverse reactions are possible. If a ball rolls down a hill, we can reverse that process by inputting energy and carrying the ball back up the hill. If a gas spontaneously fills the container, we can reverse that process by an input of energy, and we can condense the gas back down to one side of the container. If iron gives up electrons to oxygen and forms iron oxide, or the iron 2+ or 3+ ions, that can be reversed in certain circumstances by an input of energy where we drive the electrons backwards. The electrons flow back to the iron, and the iron ions become elemental iron again. In some circumstances, the reverse reactions can occur, but they always need action from the outside. Here's another example of that. Conversion of sodium chloride to sodium metal and chlorine gas. That's possible. It needs electrolysis. So it needs electricity to flow into it and force the electron transfer to go the opposite direction. Some reverse reactions are impossible. So for example, water freezes under 0 degrees Celsius, right? A phase change occurs. But that phase change is never going to occur in the opposite direction. Water is never going to unfreeze at a temperature below 0 degrees Celsius. Water is never going to freeze at room temperature and pressure. So some are impossible to reverse. Some are not impossible to reverse. And so this is where we take a step forward in our knowledge of chemistry and chemical reactions. When you were in middle school or possibly even early classes in high school, you talked about how the famous line that all my chemistry students come in with is, physical changes are reversible, chemical changes are irreversible. Well, that's just not true. we can reverse some chemical changes, and some physical changes can't be reversed. It's a simplified version. So we need to take a step forward and look at this idea of reversible versus irreversible reactions, or spontaneous versus non-spontaneous reactions on a deeper level, and understand the characteristics that make some of these possible and some of these impossible on a deeper level. So that's what we're going to do in this chapter. Congratulations. You are moving forward in your knowledge beyond what you learned in elementary school, middle school, and early high school. Woohoo! All right. It should feel good. It should feel hard, but it should feel good. Okay. So here we go. Let's talk about these thermodynamic criteria. If a process is spontaneous, the reverse reaction is non-spontaneous, and vice versa. If you come across a process that is non-spontaneous, well, the reverse of it is going to be spontaneous. So that helps us to divide this line a little bit more clearly. Again, hold up before we move forward. It's a general principle, which means it is usually true. But in all of our model building for chemistry, hopefully you've seen at this point in time, we try to build models. We try to build models to explain, and we try to build models to predict. And all of our models at some point in time break down. Under some conditions, all our models fail. So keep that in mind. This is a general principle. It's usually true. It's probably going to break down under extreme circumstances. All right. Using general knowledge, determine if the reaction will be spontaneous or not. So these are not questions that you should be able to answer only if you have a PhD in chemistry or only if you have specialized chemistry knowledge. These are things that I'm assuming you're going to have experience with. If you don't have experience with toilet bowl cleaner, you need to get some experience with toilet bowl cleaner. Go figure out how to clean a toilet. Ask your parents or your guardians if you can clean the toilet this weekend. They will love supporting your acquisition of life experience and knowledge. Okay, so take a minute, pause this video, see if you can determine if these are spontaneous or not, and then unpause and we'll keep moving forward. All right, action of toilet bowl cleaner, which is hydrochloric acid, on lime deposits, which is calcium carbonate. This one is going to be spontaneous. There's nothing you have to do if toilet bowl cleaner is on lime deposits. That is a chemical reaction that's going to happen all by itself. You don't need to heat it. You don't need to mix it. You don't need to scrub it. Although once the chemical reaction happens, you may have to scrub off that first layer of chemical reaction in order to expose the second layer to hydrochloric acid again. But this is a spontaneous reaction that will happen all by itself. The boiling of water at normal atmospheric pressure, which is 1 atm, and 65 degrees Celsius. This is a non-spontaneous process. This will not happen. In order to boil water, you're going to have to be at 100 degrees Celsius. All right, reaction of N2 and O2 to form NO2. Now, this one might have been tricky because you might think that you don't have experience with N2 and O2. How would I know if they're going to spontaneously form NO2 or not? Well, you do have experience with N2 and O2. 70% of your atmosphere is made up of nitrogen, elemental nitrogen. So you have the majority of what your hand hits when you do this is going to be nitrogen gas. 20% of your atmosphere is going to be oxygen gas, or maybe even higher than that. So another 20% of what you hit when you do this is going to be oxygen. So you have nitrogen and oxygen around you all the time. Is it spontaneously turning into nitrogen monoxide? I should hope not, because nitrogen monoxide is poisonous and you can't breathe it or you will suffer consequences. So no, this is a non-spontaneous process. Nitrogen and oxygen are not going to spontaneously form nitrogen monoxide when they're left at room temperature like we're sitting in. Thank goodness. All right, melting of an ice cube, spontaneous or non-spontaneous? And this one depends. It depends on the conditions. What are your conditions? Are you at room temperature and pressure? Well, in that case, it'd be spontaneous. Are you standing on a glacier at the North Pole and it's 30 degrees below freezing? Well, in that case, it's going to be non-spontaneous. So this one depends on the conditions, primarily temperature, possibly pressure also. But this one's going to depend. Okay, so notice the reverse of all these reactions that are spontaneous. The reverse is going to be non-spontaneous. Non-spontaneous unless some action is taken. The reverse of the non-spontaneous ones will actually be spontaneous. So we get this nice little division going on here. All right, so next question. So now we can kind of divide it into spontaneous or non-spontaneous, but what makes a system spontaneous? Well, that is an excellent question, and I'm so glad you've asked. All right, so we can start this discussion by talking about enthalpy. We just talked about enthalpy for a whole chapter, right? And enthalpy certainly seems to have an effect on whether something is spontaneous or not, right? If a system is exothermic, so think about your energy diagrams, right? We have reactants here, there's some input of energy, and then you get more energy out than you put in to reach the products. Okay, so this is a negative H situation, which means it is a exothermic reaction. And these certainly exothermic reactions tended to be spontaneous. But there's always exceptions to this, and very normal exceptions too, like the melting of ice. The melting of ice at temperature greater than 0 degrees Celsius. Well, think about it. If ice is your system, your energy is going from your surroundings into your system. That's an endothermic process, and it's spontaneous. So certainly not all exothermic processes are spontaneous, and certainly not all endothermic processes are non-spontaneous. So enthalpy seems to play a part in spontaneity, but it doesn't determine spontaneity by itself. So we need to look at a couple different factors. So put enthalpy on the back burner. It's going to play a process. We need to understand it. We need to understand its role in spontaneous processes. But let's return to it once we've talked through a couple different factors. And the first one we're going to talk about, or the next one we're going to talk about, is entropy. So we have enthalpy, which is H, right? Which is heat under constant pressure. Okay, we also have entropy. Now, why they named them two names that are so similar together, I don't know. Maybe just to mess with us all. It's a very distinct possibility. But enthalpy is going to be heat under constant pressure. Entropy is something very different. So let's look at what entropy is. All right. Entropy. Entropy is related to the degree of randomness or disorder of a system. The degree of randomness or disorder for a system. Its symbol is going to be S. It's going to be a state function, which means it's pathway independent. And it's going to be an extensive property, which means it is dependent on the amount of material that's present. So much like enthalpy, if we double our reaction, entropy for the reaction is going to double also. Okay, so entropy also plays a role in the driving force for a spontaneous reaction. Again, like enthalpy, it's not the end-all be-all for spontaneity, Well, I guess before we talk about that, we should talk about how entropy functions. So entropy, just like enthalpy, we can describe the enthalpy of the system. We can describe the entropy of the surroundings. And together, entropy of the system and entropy of the surroundings together make up the entropy of the universe. Okay, now here's where the distinction comes in. So entropy of the system and entropy of the surroundings by themselves, they don't describe spontaneity. Okay, they're a part of spontaneity, whether a process, they're a part of determining whether this process is going to be spontaneous or not. But they, in and of themselves, can't tell you if a process is going to be spontaneous or not. But entropy of the universe, on the other hand, can. So entropy of the universe, if the universe is going towards disorder, so an increase in the entropy of the universe, that is the driving force for a spontaneous process. Okay, so let's look at this conceptually and mathematically. We'll kind of break this down to wrap our brains around it. But think of it this way. If you are talking about a deck of cards, right? You throw the deck of cards up in the air. The deck of cards is going to naturally proceed toward a state of disorder, right? If you throw the deck of cards up in the air, how many times is that deck of cards going to land so that it's perfectly ordered from in terms of suit, in terms of number? I mean, it's just not going to happen, right? And so there's a tie here to probability that we'll explore in just a second. But it's a good example to show us that nature proceeds toward disorder. Think about an earthquake, okay? An earthquake hits our town, hits your house, right? The earthquake is this huge pulse of energy. Basically, energy is being inserted into all the systems inside your house. Okay, so how many times is that impulse of energy or that input of energy going to result in more order? Never. It's never going to result in more order. In order for more order to occur, we have to put our minds and our hands and our own energy to work and reorder things. It takes an extreme amount of energy in order to order things. Just ask my sweet and lovely and disorganized little daughters. If I leave them alone in their room for an hour, their room goes to chaos. Beautiful chaos that usually involves snowflakes hanging from the ceiling and every other surface in their room, right? But there's also a ton of little tiny pieces of paper that have been cut out of those snowflakes that is everywhere, right? Nature proceeds towards disorder. It's very natural. And I have to remember that when I walk into their bedroom and I see chaos everywhere that now I need to fix. Right? Okay, so nature proceeds towards entropy. The universe naturally proceeds towards entropy, towards disorder. And if a system results in an increase of entropy in the universe, it is a spontaneous system. So entropy of the universe can tell us about spontaneity. Entropy of the system by itself or the surroundings by itself cannot. It's a very important distinction to make. Okay, so here you go. Here is an equation down at the bottom for you. You see delta S there, so the change in entropy there. It's going to be the entropy of the solution minus the entropy of the solvent A, entropy of solvent B. So this is an example of the entropy change that happens when you take a salt and dissolve it in the solution. And it's always going to result in a change of entropy that is greater than 0. So an ideal solution, meaning a solution that basically obeys all of our equations that we dealt with in Chapter 4 and Chapter 11, an ideal solution is going to be more disordered than its components separately. Anytime a system occurs spontaneously, you're going to get an increase in the entropy of the universe. Now, quantitatively, we can deal with entropy as it pertains to probability. And in describing entropy, I had a difficult time describing what the concept of entropy was without introducing this idea of probability, right? So let's kind of look at that a little bit more closely. So quantitative entropy is a thermodynamic function. If you ever hear someone talk about thermodynamic properties or thermodynamic qualities or thermodynamic functions, they're talking about these concepts that we're talking about in this chapter, and entropy is one of them. So is enthalpy, and we will see a third also. And so quantitatively, what entropy is describing is the number of arrangements that are available to a system. It's very closely related to probability. You can think back to that deck of cards, right? If we think of the deck of cards being perfectly ordered with suit and by suit and also by increasing value, right? That's one possible way to order a deck of cards. Now think, how many different ways are there to disorder the deck of cards? To order the deck of cards in a non-orderly way. There's a whole heck of a lot more ways that you can organize a deck of cards in a disorganized way compared to that one possible way to organize it in terms of increasing value and suit. And this kind of gets to this idea of the more ways a particular state can be achieved, think disorder, the more ways disorder can be achieved, the greater is the probability of finding that state. So it is more probable to find a disordered state for a deck of cards than it is to find an ordered state for a deck of cards. Nature spontaneously proceeds toward the states that have the highest probabilities of existing. So that earthquake hits your house and knocks a deck of cards off a shelf. Okay, nature is going to spontaneously proceed toward disorder. When you pick up that deck of cards, it's going to be disordered. You're not going to find it in that one ordered state because disorder has a much higher probability of existing than that one ordered state does. Okay, so here's an example of exactly what we're talking about with gas molecules. So the deck of cards is fairly easy for us to visualize. Something like movement of molecules is a little harder for us to visualize. So let me walk you through this with just 2 molecules. Now, I made them different colors just so you can see the different types of states, right? So if we start with the system above, okay, we have 2 bulbs that the gases can exist in. Those bulbs are connected by a tube in the middle. And then here we have something similar to a burette. So we call that a stopcock. We have that stopper of the burette in this system of our tubes. And we can either lock it shut like we have it now, or if you look down below, you can open it. So when we open this valve and the gas molecules are free to move wherever they go, basically we can have one of 4 scenarios happen, right? We can have both of the molecules on the left side, We can have the red on the left and the blue on the right. We can have the blue on the left and the red on the right, or we can have both molecules on the right side. These are the only 4 scenarios that could possibly happen when we open that valve. So the probability of blue on the left side is going to be 1/2, right? Which would be here and here. The probability of red occurring on the left side is 1/2. So that would be here and here. The probability of both of them occurring on the left side is those 2 probabilities multiplied. So 1/2 squared, which is 1/4. We have 1 out of 4 chances of having both molecules on the left side. Okay, now mathematically think, how would this change with 3 molecules? Right? Our system would get a lot bigger real fast just by entering 1 additional molecule to the system, right? Now think about a normal balloon, right? A normal balloon doesn't have 2 molecules, doesn't have 3 molecules. It doesn't even have 1,000,000 molecules. So 1 mole of gas at STP would take up 22.4 liters. So that's a lot, right? Let's say 1 balloon holds a liter. It'd be like 22 balloons. That's a pretty decent amount of balloons. But think about the molecules in there. How many molecules is that? It's 6.02 times 10 to the 23rd molecules. It's that many molecules, okay? If you take that many molecules and you divide it by 22 balloons, you still have a ton of molecules in your balloons. Like, what did you change the amount of molecules by? Like an order of 10, maybe? Maybe an order of 10, right? That's a lot of molecules in 1 balloon. So how would this probability change if you have that many molecules inside this system? Right? So now you kind of see the magnitude of probability we're working with in terms of molecules. It's not one thing or the other thing. It's not 4 systems. Think of if your definition of ordered is having all the molecules in this system on one side, on a specific side, on a left side, think about all the other possible scenarios, all the other possible ways to order these molecules other than that one specific scenario. So again, nature is going to proceed towards disorder. Nature is going to proceed toward the systems that have the most probability, which is going to be disorder. It's not going to be ordered onto one side. It's going to be disorder. So this is the idea of entropy. This is the idea of entropy and why entropy tends to drive spontaneous reactions. It's a matter of probability, right? So if you love stats, your brain is very happy right now. Okay, let's kind of summarize this. So a system has a natural tendency towards disorder, and we just saw why that is in terms of probability. It has a tendency towards a lower energy state. You can think of a deck of cards stacked on a shelf in terms of an energy state, right? You can think of it in terms of potential energy. If we have a deck of cards here stacked on a shelf, that's a pretty high potential energy system. First of all, gravitationally, it's going to be a much lower potential energy system if these cards are on the ground. Second of all, it's going to be a much lower potential energy system if the cards are not ordered specifically. Think of how much energy you have to put in order to order the cards specifically, right? It takes you time. It takes you brain power. It takes your body digesting the apple you just ate to move your hands in order to order these cards. It's a very high potential energy state. Those cards on the floor, laying all around, all disordered, that's a much lower potential energy state. So systems have a tendency towards lower energy states. They have a tendency towards more disorder or more entropy. We talked about this in terms of a deck of cards. It's easy for us to visualize. We talked about this in terms of adding gas to a container. Harder for us to visualize, but we can see the exponential increase of probability through that system. Okay, so here's your takeaway. There are more ways, more being an understatement of the year here, more ways for a system to be disordered than there are to be ordered. Nature is going to tend towards the states that are likelier to happen, which is going to be a disordered state. All right, so let's look at this in terms of specific contexts, specific situations. So entropy will increase. Entropy will increase as solids melt to liquids. Thinking about this in terms of positional probability, right? If you give solid water enough time to lock into place, these water molecules are going to lock at a very specific distance to one another. They're going to lock at a very specific orientation to one another. You can actually look up the crystal structure of water when it freezes. You can look up the crystal structure of silicon dioxide. You can look up the crystal structure of carbon as a diamond forms. Okay, these have very specific orientations to each other, very specific distances to each other. It's a highly organized system. When these systems melt into liquid, these liquids have variable distances to each other. They have variable positions. They're sliding past each other. There's movement. So there's much more disorder in a liquid versus a solid. Same thing for a gas. A gas takes this one step further, right? Gases can be compressed. Gases can be expanded. Gases are highly moving. They're always moving towards each other, away from each other, bouncing off each other. Okay, there's a lot more movement. There's a lot more variability in that system. Gases are much more disordered than liquids. Liquids are more disordered than solids. Solids and liquids dissolve in solvent to form a non-electrolyte solution. So remember, as you have like sodium chloride dissolving into water, that sodium and chloride is going to form specific little systems around each water molecule, right? So each sodium ion is going to have a specific number of waters oriented around it. It's a pretty ordered system, right? Whereas if you have a non-electrolyte solution like sugar, okay, sugar has some orientation in it, but it's going to be a more disordered solution than the crystal structure of sugar is. Not always true for electrolyte-based solutions. So you do have to be careful about that distinction. Okay. A reaction increases in the number of molecules of gas. So if you go from 1 molecule of gas to 7 molecules of gas, think of it in terms of positional probability. Those 7 molecules now increase the probability of your system, increase the possible positions that those gas molecules could be in. So they're going to increase the possible positions of disorder when compared to that 1 molecule. We kind of saw this. I mean, think about those 2 molecules in our original system that we were looking at that looked like that. Okay. If we're dealing with 2 molecules, the probability of finding them both on the left side was 1/4. Well, if that increases to just 3 molecules, so an increase in the number of molecules of a gas, then the probability of finding them on that left side is going to be so much higher. What is that? 1/2 raised to the third, 1/8. So that you have an eighth of a chance for all those molecules to be located on the left side. So there's 8 total positions, so 7 other positions possible for those molecules to not all be located on the left side. So every time you have an increase in the number of gas, the positional probability expands, and there's more possible ways for that gas to be disordered versus ordered. So anytime you have an increase in the number of molecules of gas, entropy is going to increase. And then a substance being heated. So again, temperature for us is very closely related to kinetic activity. So if something is heated, that means it starts to move faster. Its average speed is greater. And if there's an increase in motion, increase in atomic, ionic, or molecular motion, there's going to be an increase in disorder also. So these are the scenarios in which entropy will increase. And we can use these scenarios to predict entropy. Okay, so we can look at these. This would be a good place to pause your video and see if you can predict, is the entropy of the system going to increase or decrease? Okay, synthesis of ammonia, we go from 4 molecules of a gas to 2 molecules of a gas. Okay, entropy is going to decrease here because our molecules of a gas are decreasing. Preparation of a sucrose solution. So we're dissolving, going from sucrose solid to sucrose aqueous. Remember, sucrose is not an electrolyte. It's a polar molecule. That's why it dissolves. It's not going to break up into ions and be able to carry a charge. So we are going to have an increase in entropy. Well, maybe I should go change in entropy decreases on the first one, change in entropy increases on the second one. How about the last one? Evaporation to dryness of a solution of urea. So here's urea. We go from an aqueous solution of urea to a solid solution of urea. Is urea an electrolyte? No, it is not. So in this case, the entropy is going to decrease. We are going to a more ordered solution. Change of entropy is going to decrease. Okay, so next time we come back together in class, we'll practice this concept a little bit more. Bring your questions. I'll see you in class.